these lessons, right? Irrational exponents. What are they? Right? You talked about rational exponents that were fractions, right? But what happens when your exponent is the square root of 2 or pi, right? These are irrational numbers. They cannot be represented as a fraction, right? As a ratio. As a matter of fact, they're strange because, right, they just keep going on and on and on and on forever and ever and ever. Those decimals, right? It never ends. So they're very strange numbers. What happens when they're exponents? Really, the best thing that we can do at this point is to just estimate what those are. So right here's a decimal approximation of each of those numbers. They are irrational degree. They are irrational, right? What we need to learn is something called the squeeze method. And we've done this for radicals, right? In this class, when I was estimating radicals, I would write something like the square root of 1. Sorry, the square root of 2 is between the square root of 1 and the square root of 4, right? We know that the square root of 1 is 1, and the square root of 4 is 2, so that tells us then that the square root of 2 is somewhere in between 1 and 2. It's a number between 1 and 2. And we're going to do the same thing, but we're going to write these irrational numbers as exponents. So for instance, if I wanted to estimate 2 to the pi power, right, pi is approximately 3.14, blah, blah, blah. Don't memorize that. I would rather know that it's close to 22/7. It's a much better number to memorize, in my opinion. And as we expand that decimal, we get closer to an actual approximation of 2 to the pi power. And you can put that in your calculator, and you'll see that it is indeed between 8.8244 and 8.8256. We're going to actually do the same thing, so we're going to use the squeeze method. The idea is that as you increase these the precision of your decimal places, you actually wind up getting closer to the actual value. Let's actually do so that makes a little more sense. We're going to skip. Obviously, you know how to put that in your calculator. Maybe take that. So let's do this problem. What is an approximation of 2 to the square root of 2 pi? All right. So first thing, we know if we put this in our calculator, right? And we can do that. Let's go ahead and do it. So we can put the square root of 2 in there. And it's going to give me an approximate value. It's approximate because it's rounded no matter what. The only value that you can get for that is a rounding value, because you can't really go on and on forever and ever and ever. Wait, that's not being hunted by them helping. Okay. Let's get to this. So we have this approximation. So the idea with this method is that, right, I'm going to use the idea that the square root of this, what I told you before, right? This same kind of method, that we can approximate the square root of 2 by saying, hey, it's between 2 square roots that I know, right? I know that this is 1, and I know that that's 2. So I know, just like I said earlier, right? The square root of 2 is somewhere between 1 and 2. We're going to use the same concept to approximate or estimate 2 to the square root of 2. So I know that 2 to the square root of 2 power then must be somewhere between 2 to the square root of 1 and 2 to the square root of 4, right? sludge 1 and 2. I can take it a little further out, and I can say, hey, if I know that I have this decimal approximation, I could take it one more decimal out and say, hey, it's between 1.4 and, sorry, 2 to the 1.4 and 2 to the 1.5. So that gets us a little closer. I could get even closer by saying it's between 2 to the 4.1 and 2 to the, 1.41 and 2 to the 1.42. See what we're getting? We're just, it's in there, right, somewhere, and we're getting closer to what it actually is. It's contained. So it's somewhere between 2 to the 1.414 and 2 to the 1.415. And you can see the pattern. So there's the squeeze method in a nutshell for you guys. Hey, not sure why Eureka wants to do it right now. It's like the trailer for the movie that you're gonna watch in module Module 3, topic B, where we actually look at solving exponential and logarithmic equations. We have to use this number E, Eulers number. This word is pronounced Euler, not Euler, but Euler. He is a gentleman from Switzerland. And this guy, one of the most brilliant human beings to walk the planet. Seriously. One of the most smartest people. That's right. He's the most smartest. He was more smarter. Yeah. No, he wasn't more smarter than anybody, but I think he was real smart. Interesting fact about Euler. He had bad eyes, and eventually became blind, but was still prolific in his math writing after he was blind. He'd have a scribe that would write down the stuff for him, so he would be doing a problem just with his mind, and a scribe would be writing it down for him. So he would be doing it with like crazy math. His one of the things that he really loved to do was calculate primes to come up with algorithms where you can find find the highest prime number that you possibly could. I think he found a prime number in the 100,000, which is really hard to do. It's extremely difficult. So, anyhow, we came up with this number, E. It helps us take care of natural logarithms. This guy right here. You can actually calculate it. You can go to your handy calculator, and if you hit second and ln and hit 1, it tells you what that value is. We're going to use this value when we are solving logarithmic equations with natural logs in them. Just a little preview for you. Okay? A little preview. That's all we're going to say about that for now. And we're going to move on to rate of change. So, rate of change, we can really closely relate. It is actually the same thing as your slope formula, just wrapped up in a different package, just with some difference. It just looks a little different. All right? So, Kelly and Joe are examining the population data in the graphs below for history report. Their comments are as follows. Hey, Kelly Torres says, it looks like the U.S. population grew at the same amount as the world population, but it can't be right, can it? And Joe says, well, Calliope Torres, I don't think they grew by the same amount. but they sure grew at the same rate. Look at the slopes. So, all right, how are we going to figure that out? Which one of them is right? I think we should probably look at the slope. He said look at the slopes. There is absolutely no way that the world population is growing the same amount as the U.S. population. That's crazy. We don't have that many people in the United States compared to other countries like India and like over 500 million or something like that, around 500 million. Yeah, I think both China and India have billions. Like over a billion. So, let's look at the slope of this thing then. We know that Callie is really wrong. She needs to stick to orthopedic surgery. Oh. So remember, we represent our slope as our change in y, delta y, over delta x, right? Some people call it rise over run. I don't like that because it never, you know, your y value doesn't always rise, right? Sometimes it anti-rises. It goes down. And so I like to talk about it in terms of the change of y over the change in x. And over here, this is going to be our change in y, and that's our change in x. So let's go ahead and calculate those slopes. We can estimate them because we have some number values over here on our axes. I'm going to move that up a little bit. So the idea is that I could represent these as a slope. Let's call this first one slope number 1. Remember, our slope is y2 minus y1 over x2 minus x1, right? Remember that slope formula? All the way back in algebra 1? So in this case, we can look at this thing and say, hey, y2 is probably right there, right? It's our y value for this point. So that's going to be 6,000 minus y1, which is my x value, my y value for that point, which is, I don't know, something like 2,500 probably, divided by, and our x value for the second point is 2,000, and our y value for that second point is 1950. And if I put that into my handy-dandy calculator, I come up with the result of it's just too far out. 70. So what does that mean? That means that according to this graph, the world population increased by 70 million humans per year. All right. Let's do the other one. What about our second slope? Looks like our maximum y value is around, I don't know, 275. And our minimum y value on this is 150 divided by, hey, let's represent this in a different way. And I don't know what happened. Those don't belong there. They belong here, right? Our little marky marks.
I wasn't seeing that.
Hey, can we represent this as year 0, year 10, year 20, year 30, year 40, and year 50? Surprisingly enough, we get the same answer if we do it that way, right? Because my y value, my maximum, x value is 50. My minimum x value is 0. If I put this into my handy-dandy calculator, I believe I get 2.5. So that's 2.5 million humans per year. So neither Kelly Torres nor this other guy Joe were right. Oh, maybe. Okay. I stopped watching. Moving on. Hey, we can also do the same thing with the table. So what if I wanted to find out, so I have this table of values. This is also world population growth. And I would like to estimate the increase in world population from 1950 to 2000. So we're estimating not necessarily the percent increase, but the rate.
I love that here so much.
All right. So this is how it's going to work. I have a new formula. It's the same formula using different notation. We call this our rate of change. This formula is at the end of the lesson for lesson 6.
Rate of change.
Hey, so let's call this A, and this is B. We want to know the rate of change from A to B, from 1950 to 2000. If that's A, I'm going to call this f of A, right? If we were looking at a normal table of values, we call that x, and we would call that f of x, right? So then it would make sense that if this is A, then this corresponding value is f of A. And if that's B, this is f of B. So this is like our y1. This one's like our y2, and this one would be like our x1, and this one would be like our x2. So then I can plug that into my handy dandy rate of change formula. And that would give me, I'll have f of b 6,070 minus f of a 2,519, all divided by b 2,000 minus a 1950. I believe when we calculate that, I think we get 71.02. Which means that the rate of increase in world population from 1950 to 2000 is 71.02 million humans per year. No problem, right? So your homework for this is numbers 6 and 7 on module 6. I'm going to do another example for you, though, right now. Yep. Yeah, not a skill test, but a mod. So here is a classic problem. Classic problem. They love problems like this on standardized tests. ACT, SAT, whatever test you're taking to get into wherever. Really, it's a classic test. Classic problem that you'll see on a test. I don't know why I said underground. It's not underground anymore. It's just a rocket. Sorry. This was a work in progress last period. So it's a rocket's path, where h is the time in seconds after the launch, and f of h is the rocket's height. We're asked, what is the average rate of change between 1 and 3 seconds of flight? So, just real quick, let's look at what this thing looks like. So if I was to put it into my graphing calculator, this actually looks like this. So I could zoom out a little bit, but you can see it looks like what a rocket's flight looks like, right? It goes up in the air, and comes back down somewhere, and serves whatever purpose you set out to do. All right. So let's calculate a rate of change. We would imagine that between 1 and 3, our rate of change should be positive. Our rate of change can be negative, though, right? What if we're looking at a rate of change from 7 to 8 seconds? This thing has a negative rate of change. So it's possible to get a negative rate of change as well. But let's go ahead and calculate the given one. Between 1 and 3 seconds, what is our rate of change? Well, how do we do that? Well, if we're going between 1 and 3 seconds, then A is 1, B is 3, and in order to use our equation, f of B minus f of A over B minus A, we're going to have to calculate f of B and f of A, right? How do we do that? We just plug them in there. Okay, so how's that gonna work? Let's do it. It turns out that f of A is equal to f of 1 in our function, which is going to be negative 1 squared plus 8 times 10 plus 4, which is negative 1 plus 8 plus 4, which is 11. Okay? So f of A is equal to 11. How about f of B? F of B is equal to f of 3, which is negative 3 squared plus 8 times 3 plus 4. That is the same thing as negative 9 plus 24 plus 4, which is 28 minus 9, or 19. All right, so now we know we've got our f of A, we've got f of B, we have A, and we have B. We can now plug them in here. F of B is 19 minus f of A, which is 11. B minus 8 is 3 minus 1. So 19 minus 11 is 8 over 2. So we get a rate of change of 2. I don't know, meters per second. I didn't give the original problem any units. So the rate of change is 2. Meters per second, maybe? I don't know. Oh yeah, sorry. I can do calculus, but I can't divide 8 by 2. And that's it. So that's a classic example of that. We are now currently done with that lesson. Thanks, guys.
Rock stop.
No mercy in this dojo.